And everyone will be entering now.
Welcome, everyone, to our special online event this evening, The Local and National Cost of Air Pollution, a Local Economist's Perspective, featuring Dr. Nicholas Muller, who's Professor of Economics, Engineering, and Public Policy at Carnegie Mellon University. Tonight, we have the opportunity to learn about air pollution, health, and economic impacts occurring in the Mon Valley, and I'm really pleased that you can join us. I'm Matthew Mihalik, the Executive Director of the Breathe Project. We are a coalition of citizens, environmental advocates, public health professionals, and academics working to improve air quality, eliminate climate pollution, and make our region, southwestern Pennsylvania, a healthy and prosperous place to live. And I'm here this evening with my colleague, Danny Wilson, who's the Executive Director of the Cancer and Environment Network of Southwestern Pennsylvania. And I'd like to invite Danny, our co-host, to say a few words.
Thank you, Matt. Thank you all for being here. As Matt mentioned, I'm the Executive Director of the Cancer and Environment Network of Southwest Pennsylvania. I also sit on the Executive Council of the Cancer-Free Economy. SENSPA, we are a network of over 60 organizations, and together we envision a future where people in southwestern Pennsylvania are not exposed to toxic chemicals that contribute to cancer. Yet that is exactly what's taking place on a daily basis here and around the world. We work to change this through our 4 teams: government action, collective action, healing and justice, and science, and again through our work with the Cancer-Free Economy Network. We're so happy to have you all here this evening. Thanks, Matt.
It looks like you are muted.
Thanks, Danny, for co-hosting this with us tonight. Tonight's event will proceed with a presentation by our featured speaker, Nick Muller, followed by audience Q&A. During the presentation, people can post questions in the chat so that our team can gather them for the Q&A session. People will also have the opportunity to ask questions directly during the Q&A session by using the raised hand feature on Zoom once the main presentation is completed. We request that everyone respect the speaker by allowing him to finish his talk before asking questions verbally. We're very pleased to have Dr. Nicholas Muller as our featured speaker. He is the Lester and Judith Lave Professor of Economics, Engineering, and Public Policy and works at the intersection of environmental policy and economics. His interdisciplinary research projects focus on distributional weights in benefit cost analysis, calculating air pollution damage from wildfires and economic activity, measuring the cost associated with deployment of carbon capture and storage systems in the US, and analyzing the effects of environmental policies on the municipal bond market. He teaches microeconomics, sustainable business, energy policy and economics, and environmental and natural resource economics. He has published papers in the American Economic Review, Science, Nature, and Proceedings of the National Academies of Science. Thank you, Dr. Muller, for sharing your research with us this evening. And now I will turn the presentation over to you.
Thanks very much, Matt. And thank you, Danny, and to SENSPA for having me here this evening, and to all the attendees. It's a real pleasure to be here. As Matt mentioned, I'm on the faculty at Carnegie Mellon in the business school and in the College of Engineering. Just a little bit of background about me. I grew up here in the region in the North Hills. My dad's family has been in Pittsburgh since 1900. So longstanding ties to the area, big local sports fan, etc. By training, I'm an economist, and my research develops and uses, as I'll talk about tonight, what are called integrated assessment models to measure the cost of pollution. My research has been widely published and used. I have 16,000 registered users of my models on my website that include the federal government, state and local governments, community groups, and businesses. And before I proceed, I just want to highlight and acknowledge the gracious financial support of the Heinz Endowments and, up until very recently, the U.S. Department of Energy, among other funders. And then finally, I've served as an expert witness for the U.S. Department of Justice, the states of Minnesota and New York, and for Penn Futures. So in terms of the outline of my talk, I want to cover 3 areas. The first is I want to introduce to you what economists think of when they consider air pollution and air pollution costs, sort of how we consider the problem space. 2, I want to talk to you about how myself and my research group and colleagues approach the problems associated with air pollution in terms of modeling, the data that we use, and some of the methods that we use to ask and answer these questions. And then 3rd, I want to cover some quantitative results from some very new research that will cover 3 different levels, looking at national for the US impacts, looking specifically at iron and steel in the regional story. And then if we have time, I may get to some of the emergent risks that are associated with wildfires and the impacts of those nationally. So beginning with the economist view of air pollution, there are 3 things I want to discuss here. When economists think about economic performance, and when we communicate outcomes related to economic performance, as many of you know, we use metrics like gross domestic product and gross national product and the like. And you hear these in the news and you read them in the paper, et cetera. Almost all economists would agree with the statement that these metrics are an incomplete measure of economic activity and social welfare. And for the purposes of our talk tonight, I want to focus on the fact that these metrics omit the values and the harm in a monetary sense from pollution damage. If we think more broadly, these metrics miss the incredibly valuable contribution to economic welfare from things like cooking in the home. I just cooked my kids' supper. The metrics would capture that as economic activity. If we had gone out and purchased dinner, we cook it in the home and we don't capture that at all. All we capture are the inputs. And that's a problem for measuring economic performance. And economists have coalesced around the idea that instead of tracking GDP and these gross measures, we should actually be tracking the net value of economic output that, when we think about pollution, recognizes the costs, the very important costs that these substances impose on society. So just a little bit of history so everybody's up to speed on where these ideas came from before we start taking them apart and thinking about how we can make them stronger. Since the 1930s, during the Great Depression, the US has tracked economic performance, as I said, with measures like gross domestic product. And a little Econ 101, gross domestic product consists of consumption, what you and I as consumers buy and use, investment, which are investments in capital by businesses, government expenditure and stimulus, and then net exports, imports and exports, which has, of course, been in the news a lot lately. Each ingredient in GDP is valued by the number of units that are produced and used. So if we're thinking about consumption, the number of oranges bought in a particular period of time, and we multiply those times the market price for oranges where they're purchased. So we value them, and that dollar value enters GDP. So as I said, these are very common things like cars, clothing, food, housing, et cetera. They're all valued to their current market prices. And so the provocative question to ask is, are there important goods, and for the purposes of our talk, are there bads that do not have readily observable market prices? And the answer, of course, is a resounding yes. As I just mentioned, the value of home production is one, natural resources in place are another, and then our feature tonight is thinking about environmental pollution. Importantly, metrics like GDP do not capture these values, these important flows as they pertain to economic activity. And so part of my job as a researcher and a communicator is to emphasize the importance of the fact that our standard metrics for measuring progress miss them, and to propose ways that we can improve the metrics. So there's a split in terms of how the public and economists view the metric gross domestic product. On the one hand, these are both books. On the one hand, if you consider when and how GDP was invented in the 1930s, the data availability, there were no computers. It's unbelievable. It's a great invention that this metric was developed.
Crowd and said, quote, "It was enough."
So I'm getting a little background noise.
Friends tell us.
So on the right-hand side, we have an alternative view of GDP. And just notice the author list contains 2 Nobel Prize winning economists. This right-hand side, the book Measuring Our Lives, is really articulating the view that I'll propound tonight, which is that GDP is incomplete. And so I just want you to know that these ideas are not brand new to me. I'm carrying a torch that has been carried for a number of years by economists concerned with how GDP does or doesn't appropriately measure economic activity. So when GDP does an especially bad job of measuring progress and measuring performance is when production and consumption activities produce externalities. So an externality you can loosely think of as a spillover. So it's an impact on third parties. And the classic examples are, I go and I purchase electricity from Duquesne Light. Duquesne Light works with generators of electricity that may burn coal or natural gas in their power plants. And those power plants produce emissions that come out of smokestacks. And those emissions impact people that were not privy to the market transaction between Duquesne Light and I. The important point here is that the prices I face for power or the prices I face for gasoline only reflect the private cost to the companies that are producing those goods. They don't reflect these external or spillover costs. And economists refer to this case as a market failure. And when we have those in abundance, then when we're measuring GDP, we're just measuring the market price of gasoline or we're measuring the market price of electricity, and we're missing important costs that are associated with those goods and services. So when do we think about really widespread externality? Well, as Pittsburghers, it's, I'm sure, not a stretch to think back in history, 100 years or so. This is a picture from some steel mills on the Allegheny River showing air pollution being produced in copious amounts, and spillovers here are just obvious. But it's also the case that in the modern era, steel production still produces significant externalities. And here's a picture of Edgar Thomson, in some sense, in a different way, in a different scale, producing the same sort of externalities that we saw 100 to 120 years ago. So when we think about these costs, these spillovers, some of the ways in which they manifest, in which they impose harm on society, actually do show up within markets. And so here's an example from one of our wildfire smoke episodes of a couple summers ago, when the Pittsburgh Zoo and Aquarium had to change its operations because of heavy smoke levels. And that's going to ripple through in terms of visitation and revenue. Same episode, PennDOT workers were restricted in terms of activity. That's clearly going to influence incomes. It's going to influence convenience and traffic and safety on the roadways. And those, I would argue, are captured by markets. The issue is that we don't attribute the cost back to the origin of the smoke and the emissions. However, maybe more importantly, from the perspective of measuring performance, many of these external costs coming from pollution show up outside of markets. And in particular, I'm worried, the literature is worried, the community of economists and the activist community is worried about pollution and its impacts on health. In particular, some of the more significant health events like cancers and premature deaths. There is a long-standing body of scientific literature going literally back into the late 1960s and early 1970s that demonstrates an empirical, a data relationship between exposure to air pollution and elevated mortality risk or premature death. These substances are especially dangerous for folks who have weakened immune systems. So the very young, under 1 year of age, and the very old, and populations that have pre-existing conditions. So this is just a snippet from a survey article that shows all of these different ways in which air pollution impacts, air pollution in particular, water pollution as well, impacts public health. So there's household air, there's ambient particulate matter and ozone, there's water pollution, there are occupational carcinogens, lead, all these different exposure vectors and substances that influence public health. And I find this figure just really jarring. If you look at global estimated deaths by broad cause, and you just direct your attention over to the right, you see smoking and secondhand smoking and total pollution as 1, 2. And that is an effective way to characterize the extent, the scope, and the scale of the impact of environmental and anthropogenic pollution on public health systems and public health status globally. So the important point from the perspective of how we measure growth and progress, of course, there is a very important ethical and moral point about the fact that we would like to not have our activities adversely affect others without their consent. But from the point of view of measuring economic activity and growth and progress and value, many of those health effects, save especially premature mortality risks, are not accounted for by the currently how we measure progress through GDP. And these impacts have two ways in which they translate through to the mismeasurement of GDP. One is in any given period, the level of economic output. So if we hear the federal government say GDP in the US in a given year was $25 trillion, it's actually less than that because that number is not accounting for the many, many hundreds of billions of dollars in healthcare costs and premature mortality risks that come from pollution. So that's the level. The economy is smaller than we think. And then two, perhaps more importantly, the emission impacts growth. And growth is a determinant of investor behavior, how the Federal Reserve, tracks economic health and how it influences monetary policy, and how our employers gauge compensation. I mean, the way in which people perceive the growth of the economy has far-reaching consequences. And I contend tonight, and I've shown in my research, that when you adjust for cost from environmental pollutants, it impacts growth, and it does so at times quite significantly. And so how much in the US? Well, currently, when you look at local air pollution and greenhouse gases, our emissions in the US cause damages that are on the order of $1 trillion, which is a really, really big number. And I think probably it's more instructive to say that it's about 5% of GDP. So when we think about measuring a number and communicating a number that's as big as $1 trillion, I mean, it's a million. That's just a really big number. It makes more sense to say, or it helps us gauge the magnitude of those damages by saying in any given period, it's about 5% of the size of the total economy. So that's a whirlwind tour through how economists view the issue of environmental externality and pollution costs. The next thing I want to do is to, in some sense, explain how we get that $1 trillion number, how we arrive at it in a way that's transparent, peer-reviewed, and replicable so that policymakers and other stakeholders can act on that number, can use that number. So as I mentioned in my introductory remarks, most of my research relies on what are called integrated assessment models. And it's really just a fancy phrase that is intended to say we take information and data from a whole variety of different areas of science, and we put it together in a way that tries to represent how pollution is produced, how it moves through the natural environment, how we humans are exposed to it, and what those impacts are, right? And so this circular diagram is just trying to communicate the different stages or aspects of the model and how they're connected. And I'll go through each one of these. So economic activity, think about driving to work, hopping on a bus, cooking, going to a restaurant, all the things that we do that comprise our daily life routines, economists would think of as economic activity. And many of those produce emissions. Driving is a classic example, heating and cooling our homes, using lights and electricity, all of it produces emissions, various scales and intensity, but emissions nonetheless. So economic activity produces emissions, and we get information from emissions from the US EPA and what are called the national emissions inventories, which are basically giant databases that characterize and categorize emissions from human and biogenic or natural sources. What I will focus on tonight is a category of pollutants that we call local or regional air pollution. EPA would call them criteria air pollutants. And these are things like fine particles or PM 2.5, sulfur dioxide, nitrogen oxides, volatile organic compounds, and ammonia. The data that I will work with includes all of the reported emissions of these in the contiguous US. I also track 3 of the primary greenhouse gases, and the inventories that EPA produces, and to my knowledge is still producing, are very, very detailed in terms of quantity. So how much tonnage a particular facility, Clairton Coke Works and others produce, the specifications of the facility, so how tall the smokestack is, the exit gas velocity, and what industry the facility belongs to. So iron and steel manufacturing, pulp and paper, et cetera. So these are very, very detailed databases and very valuable resources to researchers and to activists as well. We then use what's called an air quality model to tell us where emissions go once they're produced. And what I'm about to show you is just a very simple drawing of how these models work. I'll talk a little bit about how much more complex they are, but the basic idea here is that little cylinder at the intersection of the axes is intended to represent a smokestack. And again, this is just a schematic. And we use very detailed meteorological information, wind direction, wind speed, temperature, pressure, terrain, all these things, to then estimate where the pollution goes once it's released. And so when I show you results for the integrated iron and steel facilities and coke manufacturers in the Mon Valley, and I show you a plume of where the smoke and air pollution is going, it's based on the mathematical and statistical characterization of those processes that this schematic is intended to produce. So we use real world weather data, we use real world emissions data, and we use real world specifications from the facilities to then estimate the model and tell us where the pollution goes once it's produced. This is a map showing you what the model that my graduate students and I have developed. It's called AP4. It's the 4th version of a model I built in graduate school, what seems like ages ago. And this is just showing you the county annual average PM 2.5 concentrations for the US in the data year 2017. So these inventories are published every 3 years. And when we initiated the project that I'll talk about tonight, the most recent one was for 2017. So that's why I have this map. So when I began this work stream, as I said, a long time ago in graduate school, the right-hand side, the eastern side of the country would basically have looked the same in a relative sense. Now, levels have fallen a lot because of coal-fired power plant retirements. Lots of pernicious pollution sources remain. But my point here is what's really, really different now is the West. And in particular, the West is different because of the extraordinary growth in wildfires in intensity, frequency, and the resulting emissions of fine particles. And that's what's showing up here. Now, I'm not going to spend a whole lot of time on wildfires because there are local issues to discuss for air pollution. But as you know, as far as why does the West look so polluted, it's not because there's a whole bunch of new industry. It's because the West is on fire in ways that is unprecedented, and it shows up in terms of air pollution levels. So this is just a simple graph. I'll go through it quickly. When you build a model like this and you're predicting pollution levels that you're going to use to draw inferences about impacts, like, the Edgar Thomson Steelworks does this, and this in terms of public health and ambient concentrations, you really have to be sure that your model is accurate. And the way in which we do that is to take its predictions in a given location and compare them to where we have EPA's air quality monitors, which are actually reading pollution in the air. And the thing you want to compare in this graph is the dark horizontal lines inside each box. Those are the mean prediction levels for the different components of PM. So nitrate, sulfate, carbon, total on the right, and then non-primary, which is just a combination of the three. And you can see this model is very, very accurate in terms of annual averages. And it's been used, as I said at the beginning of my talk, it's been used by thousands of people and thousands of organizations. And it wouldn't be if it wasn't a reliable and accurate and credible model that's been subject to peer review many, many times. Okay, so we started with economic activity. We produced emissions. We used the air quality model to tell us where the concentrations are. We then have to assess who and what is exposed to this pollution if we're going to make our way to an assessment of impact. So when we think about exposure and measuring exposure, I just want to say there's a whole host of adverse impacts that air pollution causes on both the economy itself and people. Things like lower agricultural production. We know that sulfur and ozone impede growth of valuable food cultivars. It corrodes, acid rain corrodes man-made materials like limestones and painted surfaces. But then we start getting into the more perhaps top of mind impacts like acute and chronic illnesses and premature death. And the research, not just mine, EPA's and others, have found that mortality comprises by far the largest share of the total monetary damage from exposures to pollution, with values as high as 95% or more of the total impact from pollution. So tonight, and in a lot of my work, I focus on mortality. There's a little bit of math here, and I just want to put it on the screen so that you are aware of the link between this model and the very, very well-respected, replicated, and long-standing epidemiology work that produces that function or that equation. And in particular, you can see the names Krusky et al. And Lapoule et al. These studies go back into the 1990s, and they've been tracking cohorts of people using very highly detailed mortality statistics and very detailed monitoring data on pollution, in particular PM 2.5, to establish the data relationship, the empirical relationship between exposure to annual average air pollution and the impact, the increase in the chance of death in any given period. And what I really want you to take home from this slide is I just use that information from those studies, and I take the functions and I put them right in my model. So I am translating the concentrations from the model of PM 2.5 into risk using results from studies that have been cited by tens of thousands of people over decades. So it's a very, very well-established relationship. And to do that across the country, the model I use is fleshed out. It relies on very detailed information from the CDC and the census by county, and in cases, I'll show you by census tract. In particular, tracking population numbers, so we know how many people are exposed to pollution, their ages, in cases, their races, and their mortality rates. Which again are observed vital statistic information gathered, collected, and published by the federal government. So these are just the two studies. This is called the 6 cities study, and you can see the cohort. This is from the one of the follow-ups. It goes all the way back to the 1970s. It's been tracking people through the present century, and these are incredibly carefully done epidemiological studies by the leaders in the field. This is a little hard to see, I apologize, but you can see in the interest of connecting this webinar specifically to SenseBus, some of these health effects are directly deaths from cancers that are statistically associated with exposure to PM 2.5. This is the other study, the Krusky et al. Study. I just want to make this as concrete as possible. So you're seeing the reports themselves. Here are the impacts. Again, lung cancer showing up as among the most important causes of death that are associated with elevated exposure to, in this case, PM 2.5 and sulfates, both of which we have in this region in abundance, unfortunately. Okay, so the final piece then, when you think about going back to the Economist perspective on air pollution, remember I kept referring to air pollution cost, air pollution damage. And the way economists think about these, as I said, is a monetary penalty that is associated with some bad outcome from pollution. And so it might be healthcare expenses, it might be lost wages from absence at work. But the biggest one is how we think about valuing mortality risk. And a little bit more broadly in terms of why we attribute a monetary figure to some of these impacts. On the one hand, if we were doing benefit cost analysis or regulatory impact analysis, in order to compare the results of policy, like limiting pollution emissions, with the costs that industry and households face from the policy, to compare those two things on a level basis, we need to monetize the good things that policy does, like limiting risk. Two, and this really connects with where we were at the beginning of the talk, if we're going to compare pollution impacts and costs to GDP, well, GDP is in dollars. And so it's a much more straightforward comparison to take pollution impacts and monetize them. Remember the 1 trillion. And then compare that to GDP on level terms. So that's another reason why we value. Now, how we do this in terms of where we turn to evidence for the value of these impacts is clearly dependent on the endpoint itself. So if we have lost agricultural production, then we're going to use crop prices. If we've depreciated man-made capital, then we have replacement cost, we have cost of illness. But when we get to premature deaths from pollution, we turn to what's called a VSL, or a value of a statistical life. And I'll talk a bit about the name. It's a terrible name, but basically what it's doing is it's quantifying the trade-off that we observe people making between income and small changes in the risk of death. Now, that sounds crazy. I totally admit that. But when you stop and think about it, we often do this in our daily lives. I make expenditures routinely to enhance the safety of my existence and my family's existence. I buy smoke detectors. We buy bottled water if municipal sources aren't clean. We wear safety equipment when we do recreation, like skiing or biking. All of these are examples of how we trade off money for reduced risk of death and injury. Now, when EPA does this, and when broadly scientists do this, often we use this relationship when we observe it in the workplace. And in particular, we look at the trade-off between fatality risk on the job and wages. And then a bunch of clever researchers came along and determined that they could do this using highly structured surveys and just asking people directly about changes in mortality risk and their willingness to pay. And many, and I mean hundreds of studies have done these experiments, and they've found that when you aggregate the risk up to an expected loss of life, the VSL turns out to be about $10 million. So that's EPA's current number, amazingly, still current. And I adopt that in my model, again, in the spirit of taking existing expert scientific results from experts and using them directly in the integrated assessment model. Okay, so finally on to quantitative results. The first thing I want to do is characterize what's been happening to air pollution in recent years and air pollution cost and damage, and then drill down and talk about some local and regional issues. So remember this map. This is the predicted ambient concentration of PM 2.5 from the model. And what we do then is feed that information through exposure, dose response. We use the functions from the epidemiological studies, and then we monetize the number of premature mortalities that those functions tell us are attributable to PM 2.5 exposure. And this is what we get. In 2020, in the left-handmost bar in this chart, damages, economic damages, monetary costs from 5 criteria air pollutants amounted to $1.2 trillion in the US. And again, that's about 4 to 5% of GDP in that period. And you can see over the ensuing 3 years, damages have increased slowly over time from 1.15 trillion to 1.34 trillion over time. Now, economic growth in the market sense, traditional GDP, it always goes up and down, but basically it's been going up over this period. So you might say, well, that's just because the economy has been growing. And I would say that's true. And when we take the pollution damage and we express it as a fraction of GDP, that's been falling. And so what that means is that GDP growth, traditionally measured, has been outpacing the growth in air pollution damage. And so it's often useful to show this as an example of a case where each dollar of GDP is actually producing less harm today than it was yesterday. But then you return to the previous slide and you say, yeah, but we're still causing about 1.4 trillion in damages from these air pollution emissions. So we've still got a problem on our hands and we need to think about how to rectify it. So this is the macro picture. And what I want to do now is drill down and talk about Pittsburgh and Western Pennsylvania and our communities. So the first thing I would say is when you think about the range of land uses and cities in the US, like many cities, Pittsburgh sees significant air pollution from transportation and what I would think of as concentrated economic activity. What makes a city is the density in which people live and in which commercial and industrial agents operate, right? There's just a lot going on. So cities have more air pollution than the countryside. However, unlike many cities in the US, Pittsburgh sits at the head of the Ohio River Valley and up against the Appalachian Mountains. And what this does is it increases cloudiness, as we all know, and it also increases regional air pollution. So we've got that in some sense working against us. But we also have some factors that are truly unique to Pittsburgh that are anthropogenic. And the one I want to focus on is that we are among few metropolitan areas in the US with very antiquated and very pollution-intensive industrial production capacity. And I'll just say that in particular, what I'm talking about are the 3 facilities in the Mon Valley that we know are heavy contributors to the industrial pollution load in the multi-county metropolitan region. So what this means is that when you look at 20 years of relatively modern air pollution monitoring data, so this is not a model, these are EPA monitors that are operated in Allegheny County and EPA monitors that are operated in every other county in the country, we see a very steady extra pollution load in Allegheny County relative to the rest of the country. And it's about 25 or 30%. There's ups and downs, there's COVID, but that line on the right is very stable. And it means even though PM has fallen from 12 to 13 micrograms nationally on average, down to 10 over this 20-year period, Allegheny County is always 30% higher. And it's the 2 factors that I just mentioned in the previous slide that's a big contributor to that. The topography where we're located and our own additional domestic pollution sources that are different than many other cities. Okay, so even more specifically, I want to ask, what are the air pollution costs of integrated steel production in Allegheny County? And so I'm going to revisit the structure that I introduced a moment ago in terms of the model. But now I'm going to replace in that green rectangle, I'm going to replace generally economic activity with specifically integrated iron and steel production in Allegheny County. And we can pull this information out from the National Emissions Inventory and demonstrate the short tons, so that's 2,000 pounds per year produced by Edgar Thomson, Irvin, and Clairton for the 5 pollutants, local air pollutants that this model tracks. And so you can see for PM 2.5, for instance, and SO2, 1,200 tons of SO2 were produced in 2020 by Edgar Thomson. And these are measured emissions reported by the firm, measured by EPA. They're not estimates. They're taken directly from the EPA's official data, okay? So then what we do is we process those through that same air quality model that I discussed to estimate ambient concentrations. And here's a map of what we get. And the broader national picture shows you, of course, logically, that the biggest effects from these 3 facilities are in Western Pennsylvania and surrounding areas. So a little bit in Ohio and West Virginia and Maryland and Virginia because the wind blows. And then when we zero in on our region specifically, the tri-state region and a few others, you can see the force or the importance of prevailing wind directions in the sense that the bulk of the mass of those pollutants moves to the northeast or to the north or to the southeast, right? Because our winds prevailing are coming up the Ohio River Valley and pushing things to the northeast. So that's our impact on concentrations. Now, what do these emissions mean for public health in the region? Well, we then run the model in the rest of its phases. We have exposures and people that are exposed. We have our mathematical functions from the public health literature that I talked about, the epidemiology, and then we monetize. And what we get is a map that shows you where the premature mortality risk is elevated. And we total those up and we get a figure that suggests that the combined emissions from these 3 facilities amount to, on average, about 20 additional deaths per year. And when we monetize those, the social cost associated with that level of risk is about $225 million per year. And that's every year that these facilities are operating, okay? So 225 million seems like a really big number to me. And so what I find instructive for myself to think about how we gauge these impacts and in terms of communicating the magnitude of these impacts to stakeholders is to compare that cost, 225 million, to some of the local economic benefits that primary metals manufacturing produces in Allegheny County. And so one logical source of benefit are wages, income. And so the first row in this table, personal income from primary metals manufacturing, paid to workers, paid to executives and managers in this industry in Allegheny County. So this is a federal statistic that anybody can go and get. We just look at 2020. Income paid was $322 million. Air pollution cost was 70% of that. My pause there is deliberate. Think about the national numbers. The national numbers were 5% of GDP. Now, personal income is not equal to GDP. GDP is a bigger thing. Even if it was just for Allegheny County, GDP includes lots of other stuff, but that's 5% of GDP. This is 70% of personal income. Now, I'm just speaking to you as a community member at this point, and I'm saying, I don't know that there's a rule that says, you know, if that percentage is bigger than this or smaller than this, it's bad or it's okay. But I look at 70% and I think that's just a really, really big number. And so that incentivizes me or motivates me to get that message out and say, hey, wait, we need to think about this angle of the pollution load and the costs associated with these emissions in our community, which is a different way of thinking about it, but I think it conveys the severity of the air pollution cost. Okay. So another way that we could think about gauging these costs is to compare those costs to all of the integrated iron and steel production in the US. So there's, it's not just happening in Allegheny County. These are showing you the integrated steel mills with the black dots, a lot of them in Gary and around Chicago, Gary, Indiana. And then the pink dots are the coke facilities. And you can see the biggest concentration of air pollution from iron and steel is, in fact, southeast of Chicago down near Gary, Indiana. Okay, so then let's make the comparison in terms of personal income for our story in Allegheny County, and then look at it in Lake and Porter counties, which are the ones up near Gary and Chicago. And you can see that the scale of operations is just much bigger there. Okay, so that's the first thing to notice. The scale of personal income is much bigger. Not surprisingly, the air pollution cost is much bigger. There's just more steel, iron and steel production. And then you see a similar, very large burden of air pollution cost in Lake and Porter counties, as you do in relative to personal income, as you do here. In fact, it's bigger, which tells me that the way in which steel and iron and steel are being produced at these facilities is just remarkably pollution intensive and remarkably harmful. And we need to think about ways, and technologically there are ways to make steel in different technologies that are much, much less pollution intensive. Okay, so I want to wrap up. We've been going a long time here by just some concluding thoughts, and to remind you that from the economist perspective, the conventional systems of economic accounting, so GDP, it omits critical determinants of cost, of firm value, and ultimately of economic growth. And this is especially important for industries and activities that produce externalities like iron and steel and transportation. I think this talk demonstrates air pollution costs comprise a really substantial share or fraction of GDP. And then it also demonstrates the cost from primary metals manufacturing in Allegheny County, and it demonstrates that it's a really significant contributor to mortality risk. And then finally, the costs themselves are a really large relative to one measure of the economic benefit of that industry locally, and that's income. Thank you very much. That concludes my talks, and now I'm happy to answer some questions.
Thank you very much, Nick, for that very insightful presentation. Now let's do some Q&A. We'll alternate by having a question coming directly from the audience, followed by one that's been submitted from the chat. So if you want to ask a question, please feel free to use the raise hand feature under the React part of the Zoom field. So is there someone who would like to ask the first question?
Matt, would you prefer that I stop share, or should I keep my slides up?
It's up to you. You may want to refer to your slides, for part of the answer.
Yep.
So, yeah. So is there someone who would like to ask the question directly? If not, then I'll start through the compiled list. Okay, well, if you think of a question you want to ask it directly, please feel free to speak up. So the first question that I see here is, I understand that an analysis of pollution in big cities was able to correlate pollution with a drop in IQ or perhaps neuronal development in small children. Can you speak to the amount and types of pollution we should worry about for our children?
So this is a really interesting point. I'll begin with a direct answer, which is I too have read some of the evidence in the peer-reviewed scientific literature that links exposure to a host of environmental pollutants, including PM 2.5, to cognitive function. That includes onset of dementia and Alzheimer's following long chronic exposure, and it also shows up with acute spikes in pollution and subsequent test scores in children. So I'm aware of that effect channel. One of the dilemmas as a model builder that my team and I face is worrying about double counting. And so the classic example is we have relationships between, say, an ER visit coming from an exposure event for asthma or for a cardiac arrest, and we want to value that. But then that same visit culminates in a premature death, and we want to value that. And one of the criticisms I've faced in the past is the figures that include the short-term events and the long-term outcomes may in fact overlap. And my strategy is I just track the long-term events. And the reason I do that is, number one, they account for the bulk of the damages themselves, so you're not missing much. And number two, when you look at the magnitudes, the case for near-term aggressive action in reducing emissions is so strong without the acute events that it's not worth running the risk of being criticized for double counting when you don't get much more policy strength or urge for action by including those acute events. I just want to reiterate, it is an important impact class. It's an emergent impact class, and I am aware of it.
Thank you. Anyone want to ask a direct question? Okay, so please raise your hand if you want to do that. The next one from our list is, have you broken out the impacts of air pollution by industrial category of the contributors to that pollution?
Absolutely. So this is a great question. We've done it by sector, which is a really broad classification. Think transportation, utilities, manufacturing, agriculture. And then we've drilled down and done it at the industry level. So crop production, livestock production, truck, train, et cetera, transportation. When I started doing this work, the bulk of the air pollution damages were from power plants and cars and trucks. And that was sort of a, maybe an obvious or intuitive story or result. Manufacturing kind of came in third. But now, some 15, 20 years later, utilities have diminished in terms of their contribution to air pollution costs. And that's primarily due to retirement of coal-fired facilities, hundreds of them in the US, and the installation of nearly 400 flue gas desulfurization units or scrubbers. So utilities have come way down. Transportation has gotten cleaner, but it's still a significant contributor. The one that is now sort of stuck at the top in terms of being the heaviest contributor to air pollution damage is agriculture. And I have communicated with policymakers about this. I've communicated with my funding sponsors about this. And agriculture is just not subject to the same targeted air pollution regulation that cars, trucks, trains, power plants, and manufacturing facilities are. And so over time, those other sources have decreased, and agriculture has just maintained or gotten worse. And that's the real take-home story. The last thing I'll say about this is in the last 5 years, wildfires are now showing up as a nationally important contributor to damages, and they were larger in 2017. They were larger than utilities and manufacturing combined, which is just stunning. So Matt, I'm not sure if you see there's a hand. PJ
Yes,
Pagano.
PJ,
okay.
yeah, PJ,
Yep.
please go ahead.
Hi, Dr. Mueller. Thank you so much for that excellent talk. So, notwithstanding the political pressure that this allows us to apply, how do we leverage the cost of pollution with the industries and the industrialists? How do we, I don't know how to ask the question exactly, but how do we convince them that this is costing against their bottom line? So, for instance, insurance, health coverage, lost days of productivity. We need to get through to them because they're the most intransigent, right?
I agree, especially the traditional polluters, right? The sort of
Right. Right.
the Rust Belt manufacturers, et cetera. So there's two answers. One answer is my message is never that steel or paper or food and livestock production is bad. It's do it differently,
Right.
right? And so the example with steel is a great one. There's a research group that I'm affiliated with at CMU. A colleague of mine runs it, that is just demonstrating the radically different social cost share when you use electric arc furnaces versus primitive blast furnaces like at Edgar Thomson. EAFs are just remarkably clean when you compare them on a per ton basis to what's going on at the integrated facilities. So the message to the firms then is your capital is depreciating. Now is the time to invest. The market is moving towards those technologies. Keep up, and you'll keep us happy because you're going to reduce the pollution load dramatically. So that's one piece. The second piece is the current environment makes what I'm about to say a little less plausible. But I believe that the demand for environmental performance by major firms is still there. Financial markets, I think, are actually an important source of leverage. And up until very recently, there were a whole host of ways in which the more pollution-intensive firms in an industry faced, let's say, more challenging financing conditions than the cleaner firms within the industry. So again, let's think about Nucor versus US Steel. And that's coming through both the demand side, the investor side, but also it's coming through the access to funds side by investment banks that had been starting to prioritize access to capital for firms that were behaving well environmentally relative to others. Now, where are we now? I think we're in flux with respect to that argument. That's why I offered a heavy caveat, but I do retain optimism in the power of financial markets to move the needle in that regard.
I absolutely do. And I just want to ask quickly, um, I'm a little bit cynical about the people who run these pollutive industries. That is there a more direct way to say, listen, if you put these protective new technologies in place, you will have more productivity in your workers, or you will pay less in insurance that will offset the cost of that. Can we make those calculations?
So the modeling exercises that I demonstrate would show you, or do show you, if interpreted differently, the impairment in what a company would think of as the stock of human capital that they have access to for workers, right? It makes people sick. There's cognitive impairment that we were just talking about.
Right.
There's absenteeism. There's a whole host of adverse behaviors that are associated with these exposures. Is it enough to move the needle in terms of firm location decisions and production process decisions in the short term? I'm not sure. I think it's part of the information that one wants to present, along with what I referenced at first, which is to say, look, your competitors are moving into new technologies. You should keep up for a whole number of reasons, a whole host of reasons, not just this, that, or the other. One of those reasons is you'll face a lot less in normal times, a lot less regulatory pressure and community pressure if you do move into those less pollution intensive technologies.
Thank you
TJ.
so much. Thank you.
Good questions. And I just want to welcome our friends who have tuned in from Indiana and the Chicago area to this webinar. I'm glad you all could join as well. So the next question is, are there adjustments made for trends in the income level or so-called economic productivity of lives lost?
Oh, great question. Typically, yes. So if we're doing analyses over, 5 years, 10 years, even multiple decades, that are tracking the impacts of pollution cost, as demonstrated in this paper, we know there is a systematic relationship between income and the willingness to pay measures for mortality risk reduction. And so what we would typically do is apply, it's kind of like an inflation adjustment. uniformly across all people at a given time as we move through time. So the answer is a very succinct yes, absolutely.
Thanks. Next up, soot pollution from hospitals includes radioactive and cancer treatment incineration products that likely undergo inversion airflow dynamics. What's the magnitude of these impacts, assuming that their incineration stacks aren't above the standard hospitals despite the inversion potential?
So first thing is to say that we do have some information. I should say, I am aware of some information in the epidemiological literature about what the epidemiologists would call differential toxicity for components of PM. So there are metals, there are dusts, there's sulfate and nitrate. And some of these components in the epidemiological literature have exhibited different degrees of harmfulness per microgram than others. Specifically, the types that you are discussing, I am unaware of that information in that it suggests a different level of toxicity. The way that the question was asked and just intuition would suggest that they very well may have different levels of harm per unit emission than standard PM. So I'm not the right person to answer that component of the question. The low stacks question is a really, really good point. One of the things that came out of our modeling work years ago was if you modeled in the same location stacks with different heights. So, let's imagine, just as a thought experiment, a hospital installs a 300-foot smokestack versus its current practice of releasing those gases and particles at 20, 30, 40, 50 feet. You saw much larger damage if those were released in a city from the short stack than the tall stack. And we were able to quantify that. So what do we think of in terms of policy prescriptions? I mean, I don't think anyone wants to go around to UPMC and say every one of the facilities that's doing this needs a new 300-foot stack for aesthetic reasons. But I do think what we could do is think about ways in which the place and the technological properties of the combustion activities were changed to mitigate those effects, because burning any waste, incinerating any waste directly in a city without a tall stack is just, it's not good practice from an air pollution impact point of view, number one. Number two, it's avoidable, right? I mean, we just have to move this material out of the dense urban area, combust it in an appropriately facility with appropriate specifications to limit that impact. What I will say is, in reference to the earlier question about decomposition of impacts by sectors and industries, in a much earlier paper, one of the things we found was incineration was one of the most harmful per unit of economic activity, which is a little hard to measure for an incinerator or waste management, but the pollution impacts per unit of economic activity for garbage and waste incinerators was exorbitantly high. Because, as you might imagine, what are you doing? You're burning heterogeneous waste that you're not optimizing the temperature for all the different types of waste in the stream. And you're doing that typically in places that are right near urban areas, because that's where the waste is produced. And it was really clear that that was a bad idea.
This group asks really good questions. There's
They sure do.
a few more to come. So here's the next one. How do local Marcellus shale drilling related, as well as Shell cracker plant related emissions and their impacts relate proportionally to the three major other facilities you discussed?
So one of my graduate students, also supported by the Heinz Endowments, is writing her dissertation on the Appalachian Formation, so that includes the Marcellus. And there's two things I would want to communicate to this group. One, there are significant local PM 2.5 effects. I wish I had the number of annual deaths per year associated with those effects. I believe they're less than the 23, but I don't think by much for the entire formation in a given year. The other thing to note is natural gas is boom and bust, whereas steel production is relatively constant. And so you're going to get years in which you've got relatively high and relatively low impacts from natural gas extraction and transportation, I should say. But I believe they're in the same order of magnitude. If you want to follow up, you can find my email address right on the screen. You can communicate with me and I can go dig up that number. The cracker is relatively new. I don't have figures specifically for the cracker, but in future iterations of this work, the cracker's in the inventories, in the emissions inventories, and we could certainly model those impacts at a high degree of spatial resolution, just like we did with integrated steel.
Thanks for that answer. Hillary Lewis has her hand raised. So Hillary, please ask your question.
Thank you. This is really interesting. I hadn't seen an analysis before that translates, I think, individual facilities to like the ambient micrograms
Right.
unit, which is really useful for things like the PM 2.5 standard and other standards that are measured that way. Is that like something that's unique to your model, or how did you do that?
Yeah, so there are in the academic space, there's 3 models that do this. They all do it slightly differently. The folks that run those models are friends and co-authors of mine. One is headquartered out of the University of Washington in Seattle. Another is headquartered in chemical engineering here, just a different group at CMU, and then there's my model. And as I said, they do it mathematically and statistically. They do the exercises that I described differently. We've written papers that compare their predictions, and we all are pretty equally predictive. Our predictive accuracy across the models is pretty equal, which is interesting given how different the tools are. When I started doing this, as I said, long, long ago in graduate school, it was my charge to build a model that could look specifically at facilities, because I was working under a grant that one of the key deliverables was the economic accounting that I presented at the beginning. So we were developing this model. And the thing we were charged with by our funders was to develop a national air pollution cost estimate and relate it by industry, and then for the macroeconomy to output or GDP. And when you're dealing with air pollution, you just can't do industry averages or national averages, because the impacts per ton of emissions are so different depending on whether a facility is out in the exurbs or in a dense city. They're, orders of magnitude 10 times different in terms of impact per ton. So we had to be very careful about how we built this tool to reflect those differences. And so what you're seeing now is the 4th iteration of that. And there have been lots of improvements and changes along the way, but it's based on that perspective that in order to measure the impacts of these pollutants correctly, you have to know where the facilities are, and you have to build the model to be sensitive to the differences among the facilities.
Thanks for that. Next up, have you looked at the pollution per job across different industrial categories?
Per job? No, not per job. I think we could. There's 2 things to say about the employment story. One is in reference to the natural gas question a moment ago. One additional finding that comes out of my graduate student's PhD dissertation is that the economic value of even the employment effect from the natural gas boom in the region goes elsewhere. And we have data that tracks where workers live versus where workers work. And so you know the number of workers in a given place who are working in natural gas and where their permanent residence is. And we've shown that it's a 2-to-1 effect, 2 times more jobs for non-local workers than local workers. Couple that with the notion that the air pollution from the natural gas extraction all stays here, and you could do, in a sense, you could answer the question you just asked, right? Which is to say, for every non-local job, what is the cost from air pollution locally? And that would be a nice calculation. The other point on jobs and pollution is yet another PhD student of mine who's now graduated and works for the Michigan Public Utilities Commission wrote in his dissertation a paper looking at the relationship between job losses from coal-fired power plants and avoided pollution damages from those same retirements. And what he found was you could replace the wages that were lost. I believe the number was 7 times over every year with the avoided impacts from pollution. So if a government or a social planner said, we are willing to transfer those lost avoided mortality and health costs to the communities that have lost workers, for instance, until they're back on their feet, you could do that on par or up to a factor of 7 times, and still society would come out with positive net benefits. And that just tells you not that the workers weren't paid enough, the wages at coal-fired power plants were actually quite high, but rather the avoided pollution costs were astronomical coming from coal-fired power plants.
Super. Next up, this one's from our friends at Industrious Labs. What are the major differences between your model and Cobra? Industrious Labs used Cobra on Edgar Thompson and Clairton and got higher mortality numbers.
So a couple things. One, when we looked at the entire fleet of integrated iron and steel mills and coke, our numbers were about 1/8 lower than what Cobra published or what Industrious Labs, I believe it was Industrious Lab, published using Cobra. So given the uncertainties associated with how we value impacts, what dose response function we use for mortalities, and the underlying differences in the air quality model, the results were really quite similar. I didn't see Industrious Labs impact estimates for these particular facilities. So Cobra used to be calibrated to what are called Gaussian plume models. And Gaussian plume models are just a statistical representation of how air pollution moves throughout the natural environment. And AP4 uses the same approach. I'm sure we're using different sources for our meteorological data and some of the underlying parameters and assumptions about wet and dry deposition. Sorry, we're getting a little technical here, but how pollution actually falls out of the atmosphere, et cetera, that would lead to differences that are on the order of the differences that I saw for the entire fleet.
Thanks. The next question is coming from the recent information that U.S. Steel has applied for exemptions from hazardous air pollutant emissions standards that were new from last year, and how your model, how those air toxics fit into the picture of your model for something like benzene or other sorts of things, and how that's accounted for or not accounted for, or what do you think that would do for the results?
So in the interest of full disclosure, this model works with CAPs or criteria air pollutants, not HAPs or hazardous air pollutants. And we had pursued some extensions of the model some years ago to move into HAPs and lead, and have not followed through or carried through on that. It would be a very interesting extension. What I would say is, to my understanding, the atmospheric processes, and I'm not talking about wind and the things we already have, but rather the chemical reactions that are associated with an emission of benzene and others, are really different than what we currently have the capacity to model in AP4 with respect to, say, secondary PM formation. And so it would be a big lift to expand AP4 or build a new AP4 to include HAPs. And we're not there yet. What I would also say is, when I have seen, and this is only a comment about existing information, not whether you can take it to the bank, that when EPA has done it's what are called Section 812 analyses of the whole Clean Air Act, which include HAPs and CAPs, that the premature mortality effects from PM and tropospheric ozone, the caps, just dominate the benefits from the hazardous air pollutants. Now, again, that doesn't mean those reports aren't missing something fundamental about the hazardous air pollutants. And in fact, the benefits and damages are much bigger. But from the evidence that I've seen, it suggests that the criteria air pollutants, particularly PM mortality, is much, much bigger.
Super, thanks. This next question is, what regional areas did you consider for income-derived benefits from the steel industry? This person wonders whether the income benefits actually go to the most polluted areas, or do they go to adjacent counties further from the pollution sources?
Yeah, really neat question. So in this case, in this analysis, I just did a very simple comparison of workers, and by workers, I mean any compensated individual in the industry, so primary metals manufacturing in Allegheny County. So anybody deriving compensation in that industry that is not in Allegheny County from activity in Allegheny County. So maybe someone lives in Westmoreland County or in Beaver County and commutes. It's not going to be counted. So that doesn't mean they shouldn't be counted. It just means in this very simple comparison I did for the purposes of this talk, I just tracked the income flows in Allegheny County. There are clearly other ways that one should and could estimate the value of the positive economic stimulus that these facilities and that economic activity has provided for the region. Would it double the primary income or personal income? Would it triple it? Even if it did, we're still talking about a pollution share that's 35%, that's 17% of that measure of economic benefit. And to my mind, anywhere above, 2, 3, 4, 5% is a significant social cost load. So just in summary, yeah, this is a really good point. Compensation in Allegheny County is a narrow measure. It could be bigger. It might be a little hard to measure, but it could be bigger. But even if it's way bigger, I apologize about the dogs. Even if it's way bigger, we're still talking about a pollution cost load that's a really high fraction.
Thanks. Next question is this research published? Can we get a link? Okay, great.
Yep.
Then
So
go ahead. Yeah.
This particular study is not yet, it's in process. Much of my work and certainly work with this model, for instance, the reference to the work on power plants and workers' wages, et cetera, that's published. I'm actually happy to respond via email if there are questions about papers. I'm happy to send those. The plan is to write an article about this set of experiments for local popular press, and then from there you would have access to all you need. If you go to my faculty webpage at CMU, you'll see a tab for the model. And if you go to the model and sign in, you have all the data you need. It's all there. It's all publicly available. It's all free. So.
Thanks. Mark Dixon has his hand raised. So Mark, you're up.
Yeah, thank you so much. This was just a great presentation. I'm curious about other types of benefits. You focused in on income. I'm thinking, like, I often hear in town hall meetings and things like that the municipalities are worried about losing their tax revenue.
Yeah,
and I wondered
right.
about that kind of revenue, and then other types of revenue that I haven't heard of, but seem to be manipulating the decision process across the Mon Valley in ways that I don't fully understand. So I wondered if you could speak to those other types of income and how, if you have a gut check on whether they may be largely different than income.
Yeah, so I think my reply, this is a really important point, and my reply is similar to the one I gave earlier, which is to say, we know that a big capital intensive and to an extent labor intensive installation like Edgar Thomson or one of the others has positive economic stimulus that I didn't measure, right? And when workers earn income, they do things with that income in the local economy that frankly gets tracked in GDP, right? They consume and they invest, et cetera. And I've always been a little skeptical of efforts to measure that, only because it's really, really hard to measure, right? That sort of secondary spillover economic stimulus. But it is there. How big is it? I don't know. But as I said, if it's 2x, I would be surprised. But if it is, then we're still at 35%, right? The tax revenue piece is a very, very good point. And I don't know, but I'm wondering if I could dig up or if the records exist such that one could gauge the magnitude of the contributions to local tax rolls by these facilities and the owners of these facilities. Because then presumably those tax revenues are being invested in local public goods, roads, schools, et cetera. And that's really important. And I'm certainly not saying it's not. I am saying, A, this is a great suggestion. B, I might be able to go track it down and see a really comprehensive measure of that denominator, if you will, when we're comparing social cost to value of production, local value of production. It should include these metrics.
Thanks. The next question's from Marilyn. She asked, ambient air quality sometimes has or shows short-term spikes or high levels. Are there studies that help determine the health impacts of these short-term acute pollution incidents?
There are, and there's a really significant literature that tracks these. So I would encourage thinking about the epidemiological literature in two categories. There are the long-running cohort studies that track, in the case of the two studies I was referencing, tens of thousands of people over long, long periods. And they track their exposure to some summary statistic of pollution, like an annual average or a quarterly average, and they track them over time. Then there are studies that do exactly what the question referenced, which is we're tracking, say, hospital admissions or daily deaths in a particular location, and we're associating that with today's pollution, yesterday's pollution, 2 days pollution, 3 days lag pollution, et cetera. And there's a bunch of studies that do this. And they also find an effect of pollution on death counts at hospitals. However, when you look at the effect size, the long-standing chronic exposure, quote unquote, cohort studies are about 10 times bigger in terms of a percentage effect. So a 1 microgram per cubic meter impact of increase of PM 2.5 has an effect, if it's an annual average, that's about 10 times the size of a 1 microgram per cubic meter spike in a day. And so I fall back on my, I don't want to be accused of double counting crutch, if you will, and say, I used to look at both. And then there was a clear argument to say the acute stuff was subsumed in the chronic stuff because the statistics literally are tracking the daily deaths. They just compress it into an annual average. And so I don't track the acutes. There are models out there that do track daily levels of pollution, and they're used for things like NAAQS compliance, air quality compliance, associated with things like pollution episodes at Clairton and other facilities. My model just isn't designed to do that.
Thanks. We've got about 5 minutes left, so a couple more questions. This one is about your model, and the question is, you use the National Emissions Inventory data as inputs to the model. Are there any ways, has anyone ever measured if those reported results undercount actual pollution compared with monitored data? And if so, what might be the impact on your model?
The answer is yes, and it's overcounting and undercounting. The way that these tests are run is very important to consider. And so I'll lay out how this is done and then point out maybe some of the potential questions they raise. So my model is, by all accounts, pretty big computing wise, computing load, lots of dimensions. It's a pretty complex thing. But in the space of air quality modeling, the tool I use is very simple. And the tools that other folks use that track individual parcels of air minute by minute as they move through the atmosphere take very, very long periods to run just for one scenario, right? And by long periods, I mean hours and days, and they cost lots of money to run. And so you just can't do the source specific stuff that I do with these big models. However, what those models will do is they will be used to take emissions and predict concentrations at locations that are exactly where the monitors are situated. And they will use those models to try to verify the emissions data based on the differences between what the model suggests is happening at the monitor and what the monitor suggests. Now, I think the obvious criticism here is that you're relying on an assumption that that model is near perfect. Because you're sort of by backwards induction saying if the discrepancy at the monitor is happening, it's not because the model's wrong, it's because the emissions data is wrong. Which, you know, I joked with my air quality modeling colleagues about that perspective, but those models are very, very good at what they do. And so that is one way in which scientists are trying to assess the quality of the emissions data. An emergent area is using satellite information, right? So on clear days and nights, you can use remote sense data to view pollution plumes at very high degrees of resolution, you know, a few feet square. And at that point, you're looking at the top of a smokestack. And if you're able to link the opacity and the what's called the optical depth to emissions, then you can ascertain whether reported emissions are agreeing with what the satellite is seeing from the top down. And the satellites are not operated by the same firms that run the facilities. You don't have the sort of conflict of interest concerns. And so that's another way that this is happening. I would say the third way is to use unofficial, if you will, pollution monitoring technologies around facilities to try to gauge emissions that are augmenting what the official EPA monitors that are used for compliance are doing. And so I'm thinking about the purple air monitors, the pollution monitors that Professor Presto developed at CMU, some of the mobile monitoring devices like his mobile van. All of these are ways to empirically assess air quality in ways that don't rely on A, emissions data, or B, official EPA monitors to try to get just a different empirical view of what's going on.
Thanks. So we've just maybe some rapid fire here in the last minute. Where's the best place to buy a house in Pittsburgh based on air quality?
A hilltop.
Hilltop.
Yeah. So if there's one pattern that I've seen, and this actually specifically references Dr. Presto's work, the highest pollution levels for PM 2.5 and some of the others are in our industrial corridors. And so those are almost always down by the rivers or in some of the major tributaries heading into the rivers where the roads, where the railroads, and where the production facilities are. And so of course, there's variation across the hilltops. But when you look at the difference between being 500 feet up on a bluff versus right down on a river, it's significant. And so that's what I would say.
Another rapid fire one. This is about the potential for Nippon Steel to purchase US Steel and to bring a pyrolyzing waste process to operate the steel plants. And if this happens, you know, what might be some of the consequences of that?
So I'm not the right person to ask and comment on that specific technology. What I would say is if we just step back and consider that Edgar Thomson was built shortly after the Civil War, and we're still running this thing in an incredibly pollution intensive way in an incredibly dense urban area. I just don't think that makes any sense. Now, am I saying that we shouldn't be making steel in Braddock? No, it's not at all what I'm saying. You know, the employment, the stimulus, the income, all of that is important. I'm just saying we can do this better. Why are we not doing it better than with a plant that was built in 1875?
Super. Well, we are at time this evening. Any final questions, we'll gather them and get responses back to people. I want to thank you, Dr. Muller, for your presentation and your thoughtful answers to this intense Q&A session. I want to thank the SENSPA team, Danny and Andre, for their partnership for this event and for co-hosting it. Also, Andre for his adept management of technology, for the Breathe Project team, Deb and Natisha for managing the Q&A. We want to thank the Heinz Endowments for the support that made this research and this event possible. And I'd like to thank you all for participating this evening. We really appreciate your coming on a beautiful evening here in Pittsburgh and hopefully a nice evening in the Chicago area, and look forward to following up with you all. So thank you all so much, and best wishes.
Thanks, everyone.